Thank you so much, Ravi, for the really kind introduction. And thank you for the rest of my committee, John, Repi, Sean, Lou, and Blazer for being here today, and all of you. And so we're going to talk today about tangible values with text, explorations of bimodal programming. So when people sit down and use computers, most of the time what they're using is direct manipulation. And that's the paradigm where you just click on the item you care about, you move it around, resize it, etc. And that's the standard way that people operate with computers. Drawing applications work the same way. You just click and move stuff around, change the things you want. And that's actually just so common. That's just the way people are used to interacting with computers. When they think computers, they think direct manipulation, even if they don't use those words. But there's one application that seems to be resistant to direct manipulation, and that's programming. In programming, you just write tons and tons of text. It's kind of imaginary what the text does. And then when you run the code finally and you get some output, if it's wrong, you can't just click on the output and fix it. So that's really the subject of this thesis today. Can we directly manipulate our output of our programs to fix the programs or even to build the programs to start with? And in fact, this isn't a new idea. People have been working on this for a long time. It's been tried before. So we gotta go back and think about what's going on here. This line of research is called programming by demonstration, where you give a step-by-step demonstration of what you want the computer to do. So here's an example from the Mondrian system. He is trying to demonstrate to the computer how to turn this blue rectangle into an arch. So he's given a bunch of steps to do so. And then the computer will try and infer a program from that. Right? And this research goes way back all the way to 1975, has been applied for several domains, including game design, as well as web scraping more recently. Right? So when I say there's been a lot of work on this system, in fact, there's 2 old books that have been written on it. They're holding up my laptop right now. Have any of you ever written a program using programming by demonstration? And why hasn't this taken off? All right, so there was a nice little article written by Tessa Lau. She reflected on her years of building programming by demonstration systems, and she gave some principles of what might be going wrong. And so to think about that, let's think about a worst case scenario for programming by demonstration. Say you got a blank program, you do some manipulations to show the computer what you want, but then the computer just says, I don't have any clue what you did. It doesn't make any sense. And now you're just left in the dark, right? Maybe you did do a demonstration and you got a program, but the output is wrong, and then you're like, wait, why is the output wrong? And you try and figure out why, and oh no, I don't know why, because whatever it inferred from my steps is kind of hidden from me. Maybe it's a black box machine learning model, right? So maybe we can do better than this. So here's Tessa Lau's 5 principles. You want to detect failure and fail gracefully. So we want to be more fine-grained than just, oh, it failed or oh, it didn't fail. You want to make it easy to correct the system. So if something goes wrong, you don't want to have to redo the whole demonstration. You want to encourage trust by presenting a model the users can understand. So you want to actually tell them somehow what the computer inferred. You want to enable partial automation. You don't want to force people to always use the demonstrations to create their program. And then finally, you have to think about the value of the automation you're providing. If it's not going to provide a lot of value, people just aren't going to use it because there's a mental cost to switching between the modes. All right. So let's think about how we can reimagine programming by demonstration to try and satisfy some of these principles. So instead of a black box machine learning model, we're going to represent the program as an ordinary programming language. And that ordinary programming language is always going to be text editable. So it's just like the programming we're used to today. It's going to be at least as powerful as that. But instead of just having the programming we're used to today, you will also be able to manipulate your output, and that will induce changes to your program. But if you don't want to manipulate your output, you can just text edit as well and have that change your program's output. And you can freely mix and match these modes at any time. So you're always able to manipulate the output and you're always able to edit the code. And we call this bimodal programming. So let's see, just thought exercise, is this going to help us? In bimodal programming, are we going to fail gracefully? Well, one thing we can do is we just make sure that we do small steps. So you do a little demonstration, you get a little result. So that way, if something fails, you're not stuck. Make it easy to correct the system. Well, it's always text editable. If something goes wrong, you're never stuck. You can just do regular programming to fix it. Are we going to encourage trust? It's an ordinary programming language. It's unambiguous. Partial automation. Well, you can write the code, or you can do the output, or you can manipulate the output. And then the last point is a little bit harder to talk about. How are we going to make sure these manipulations provide value? And that's somewhat the focus of the thesis, is we're going to try and see if we can provide enough manipulations that you could build most of your program using just the direct manipulations, right? So,
Brian, do you mind if I interrupt and ask a background question?
yeah.
So you've described how there are like kind of a lot of these programming by demonstration techniques that, as you pointed out, haven't really, had maybe so much practical impact yet. But there's also kind of like a, long line of work in something called programming by examples. And so maybe you can explain to me and others kind of what is the boundary between demonstration and examples? Because it seems like in, in techniques that work by example, there are kind of more use cases, it seems like, in practical life, like in Excel and various other places. So what's the kind of like boundary here, and how are these two sets of techniques related or not?
That's a great question, and I don't think there is necessarily a hard boundary. You'll notice that the title of these books, the subtitle on this one is Programming by Demonstration, and the subtitle on this one is Programming by Example. There was no distinction between them for a while. I tend to think of programming by demonstration as more of step-by-step demonstrations, like you show this step, then this step, then this step. And then examples is you provide, instead of showing steps, you show a bunch of results, like a list of results, and then the computer tries to infer from the list of results. So the line between them isn't bright. It's not a bright line.
And so if we were going to agree that, well, let's say programming by example has had more impact in practice, at least recently, like are the principles that Tess allows describing for PBD systems somehow different than PBE, or?
No, but yes. And so, I mean, when we say what is programming by example then has impact on, and the example we're thinking about is flash fill in Excel, you can start doing a transform in your cells, and then it kind of guesses what your transform is. And I think, one of the things they didn't have for a while, and I think they're working on it, or maybe they have it now, is like a description of what the actual program is that it produces, right? I don't remember exactly. Right, and that would be something where the principle does apply, because you need to be able to tell users what kind of program is produced there. Does that answer your question?
Oh yeah, great, thanks.
All right. Okay, so bimodal programming, we have some hope it might satisfy these principles, but we want to see how far we can push it. We don't know how expressive direct manipulation can be for creating programs. So that's the subject of this dissertation. Can direct manipulation of output be pushed so far that we can do general purpose programming with it? So for this presentation today, I'm going to demonstrate some of the systems that we built to answer this question. The first one's called Sketchup Sketch. We're going to try to answer a sub-question. We're just going to focus on programs that draw shapes and see if we can create those by direct manipulation. We're going to breeze through that because the committee has seen that before. But then we're going to focus most of the presentation on the new system, Manipusynth, where we're trying to say, can we directly manipulate the output for general purpose programs and use that to build programs? And then at the end, we're going to talk about a couple supporting mechanisms very briefly that we built. One is for direct manipulating custom visualizations, and the other one is for direct manipulating expression text. And you could imagine these things would be helpful in some future ideal programming system, although we didn't integrate them completely yet. All right, so let's first talk about Sketchup Sketch. Can we make shape drawing programs by direct manipulation? So here already in the first screenshot, you can see an example. This is kind of about the limit of what we can do with Sketchup Sketch. On the right here is a fractal, and we built this fractal entirely by manipulations on the canvas here. We didn't do any text edits in the code here, but you can see the code is actual code. There's actually a program behind it. We won't go through over that example, but we do want to talk about, what people have done before. So the simplest version of manipulating output for shape drawing programs is just being able to move and resize shapes. And so there's several systems that have done that, where you can just move and resize a shape and it will change one number in the program. Now you still had to write your program to begin with, so it didn't help you with the program construction there. There are a couple systems that let you do a little bit of program construction. You could add new shapes to the program, but none of these systems imagine that you could take the entire shape drawing process and make it work entirely via the output. So that's what we were trying to do in this system here, is see how far we can push it. And just as a review of how the system works, we'll make our Lambda logo here. So here's the Sketch and Sketch interface, just to demonstrate that it's a regular programming language. I'm going to start by text editing. I'll make a rectangle definition. Run the program doesn't actually show up until you use the variable in the shape list. But there we go. But once the shape is in the output, here. Once this, oops, no. One day I will learn how to manage videos in Keynote. There we go. All right. Once the shape is in the output, you can drag it around, and that changes numbers in the program. So you can see the position in the program is actually changing on the left over here. And then, sorry about that. There we go. And then we can also resize it as well, and that will change the width and height. All right, but let's delete that shape, and we want to do this entirely on the output. So we'll just draw the shape, and it's added to our program, just like in a regular drawing application. Edit a definition for us. We can change the color of that shape, which we're going to do now. All right, and then now we need the lines. So we'll draw one line, we'll draw the other line. Oh, we'll actually not draw the other line, but we want the corners to be coincident with each other. So we're going to select the endpoint of the line, select the corner, and then we're going to invoke a tool called make equal, and that will introduce a variable that will be shared between the shape, the rectangle and the line. Right? So you can see that that variable there is used for both the square and the line. And then we can snap the other endpoint as well, select the corner and the endpoint, make them equal. And in this case, it actually inserts the math that's required. So it's the x plus the width and the y plus the width to snap the line to the end of the corner there. There's a faster way to do it. When you initially draw the line, you can actually snap right away when you're drawing, and then it'll constrain them together. Now we're going to make sure the line colors are always the same. Make them black. Then we're going to group the shapes together, kind of like in a graphics editor, you can group shapes. So select the shapes, then group them. Now in a programming language, what's a group? Well, a group is just a list. So here, all it did is just put them in a list. We made a list of our three shapes. We can select the list on the canvas, rename it to say logo. And then now we're actually going to turn that list into a function that produces our group. So we'll build a function. We will build a function. There we go. You can see that now we are calling the function here with the logo func, with the y position, x position, width, and the color. We can focus the function on the canvas like so. We don't like the fact that y is before x. We'll reorder them. Maybe we'll change the parameter name to line color. And then now Sketchup Sketch uses type inference and figures out that because we're giving it a position and a width, it's drawable. So we can choose it from our toolbox and draw more copies of our function, which just inserts new function calls into our program like so. All right. So that was a brief review of Sketch and Sketch. And we were able to create 16 designs entirely by direct manipulation interactions on the canvas without editing the code, although the code remained editable at any time. And the way we were able to do that is that we offered a large amount of tools to work with. Tools for drawing, relating, abstracting, and refactoring shapes. And then also, we didn't just show the final output of the program, we also showed particular intermediate outputs within your program. So if there was a point in your program, it would show up on the canvas. If you ever added something to an x-coordinate, it would show up as an offset on the canvas. And also there were borders to manipulate and select lists, as well as function calls. So if we can make all the designs by direct manipulation, why are we bothering to even show the code at all? Well, back to TestAllow's 5 principles, we want to make it easy to correct the system. Text is flexible. You know, we made these 16 examples because, hey, we were able to, they fit within our tool set, right? There's still things you want to do with text. And then finally, we want to encourage trust by presenting a model that users can understand. Text is always unambiguous. Here's a great example of that. If I have a branch like this, a is less than 10, then draw a rectangle, otherwise draw a circle. Well, how in the world do you represent that on the canvas? There's a reason for we have code. All right. That was a brief review of Sketch and Sketch. We had tools for drawing, relating, abstracting, and refactoring shapes, along with manipulable intermediates, and that allows us to create a wide variety of programs just by direct manipulation on the canvas. So that's evidence that we can create shape drawing programs by direct manipulation. Now let's talk about manipsynth and see if we can take some of these ideas and move on to general purpose programming.
Ryan, can I interrupt and ask a question before you transition? So let's say that, you know, some rich company wanted to put 100 developers to actually, you know, build a, you know, practical shape drawing tool, you know, think like Illustrator or something. So do you think that, like, you know, based on, you know, kind of what you've discovered, are the techniques ready to kind of say, okay, let's actually build, you know, something with 1,000 features that come with a, you know, normal drawing editor in this way, or are there still fundamental roadblocks?
That's a good question. I think, you know, I've thought about this if I was going to spend the next 5 years of my life on Sketch and Sketch, what would it look like? A lot of the choices we made in Sketch and Sketch were because we wanted to see how it relates to general purpose programming. And so sometimes those are a little bit at odds with making a tool that's really good for artists. So you'd want to say, okay, I'm actually going to make a tool for artists this time. And so you'd sit down, and that would actually cause you to have probably a different set of goals when you did it. So it's a hard question to answer. But I think one thing I would want to see is like more fundamentals of space in like a type system or something like that, about things being on a 2D canvas. I think there's ways you can get dare I say grammar of graphics, but something like that. That was a very vague answer. I don't know if you want to say more on that.
I guess maybe, I mean, it is a hard question. So I think, what you've described, I think is, a good way to think about it if one was going to try to build on it. I guess one maybe follow-up question is, you showed that kind of like table or menu of tools that, you added to support these kind of 16 examples. I mean, I guess it seems like maybe one of the potential promises of bimodal programming is that you might be able to, build a rich GUI without having the kind of like super nested, 25 million menus that you find in existing GUIs. And I guess I wonder, like, based on the kind of experience so far, do you think that that goal actually is feasible, or do you think we might end up still having, these super heavily nested populated menus with so many different tools that an expert needs to learn? Or do you think there is a hope for like maybe a smaller number of more general primitive building blocks in these future bimodal systems?
Better primitive building blocks, yes. Yes, I do think there's better primitive building blocks for graphics probably out there if you sat down and thought about it. Whether you could avoid the plethora of menus, the answer is actually probably not, because once you have a programming system, it makes it easy to create functions, which means now you have to have a menu that can call it. That function you just created is now going to be a new menu item, etc. And so you're going to end up filling up your menus with your own tools.
Okay, great. So I'll try to convince you to stay for another 5 years, but that'll be a topic for after your presentation.
All right, let's talk about can we directly manipulate output to facilitate general purpose programming? All right. So we're going to talk a little bit more about this. We'll talk a little bit about the goals, go over a demo, maybe a demo and a half, a little bit about the implementation, how we evaluated it, and where it's going. So what do we want? We want code on one side of our editor as before. And this time, instead of the shapes in our output, we want to have the program's internal values on the other side. Somehow we want to manipulate those and have it change the code. How is this going to work? Well, there's been some systems that do a little bit of this. So there's like a Haskell notebook where you can maybe do some copy paste operations. But a couple of recent works where you can actually do program synthesis inside code that you're writing and have it generate little chunks of code for you, where you give it some examples of what you want. And then more closely related, there's a system called Albus Live, where you can demonstrate array algorithms, iterative array algorithms on a canvas, and it will give you textual code. But our actual primary inspiration here is a little bit more in the functional programming realm. It's Kono-Elliott's ERA system. In Kono-Elliott's ERA system, it's a 2D canvas with tangible values. So what we're actually looking at here are 3 tangible values on the canvas. So here's one, here's another one, here's another one. These tangible values are partially applied functions most of the time. And we see the function output on the bottom and then the unapplied values on top. But there's example arguments for the unapplied inputs. So, so we still get an output here. So what's happening here is we're going to take the output of this function here, and we're going to use it as the second input for this function here. And then when you compose these together, you get a new tangible value where this output's been used for this input, and then the remaining unapplied arguments are above it. So what's interesting about this system is that it showed that there's a complementarity between nonlinear editing and functional programming, because in pure functional programming, you don't have to worry about state, so you don't have to worry about time, which means that you can just throw everything you want on your canvas, not really worried about the order, and then assemble it later. And we really want to embrace that. So that's So these are our first two things we want out of our system. Of course, we want it to be a live system that's always showing you what your code is doing. But then we want to be able to gather the parts you need and then assemble them later. So we want it to be nonlinear. What else might we want? Well, we talked a little bit about programming by example. What's programming by example? It's where you give some examples of what you want the code to do. So I'm going to say, oh, I don't have a length function yet, but I want to say length of the empty list is 0. I'll tell the computer the length of that. The second list here is 1, and the length of this list here is 3. And with those examples, I don't have a length function yet, but maybe the computer can guess one for me and produce the length function we want. Where it writes this code here where it says, hey, I have a list. If the list is length 0 or empty, list is empty, it has length 0. The list is non-empty, it's 1 plus the length of the rest of the list. Right. So we want to have synthesis now that we have live values. There's something to assert on. And then finally, as with Sketch and Sketch, we want this to be a bimodal system. So you can always text edit if you need to. So we're making a direct manipulation system with synthesis. Let's call it the magnificent manipusent. Here's what it looks like, and it's going to meet our goals. So to demonstrate how manipusent works, let's first talk about how we're going to represent tangible values. Kind of the paradigm for manipusent is that one let binding in your program is going to correspond to roughly one tangible value on your canvas. So here I have a let binding where I say the variable length 3 is length of this list here, and on the canvas it looks like this over here. We have the expression on the top with a green background. Below it is the actual result value of that expression, 3. And then if we bound it to a variable name, we have the length 3 pattern is shown in pink. So that's how tangible values are going to look on our canvas. Best way to understand this is just to do a demo. So let's go ahead and do this. And if I have, go. All right. So on the left of my screen is Visual Studio Code. I have the OCaml language server installed, so you'll see syntax highlighting as well as type hints appear. And then on the right of my screen is manipusent. It's just running in a web browser. There's a little web server running on my computer that's watching this file on disk. And whenever this file changes, it'll update over here as well. So you can edit in either mode. But of course, we're going to do all of our manipulation over here. So this is the top level of our canvas. We can just double click anywhere to just begin inserting code. I'll type the open bracket and give you some autocomplete options for what I might do with open bracket. I will give an example list because whenever you are editing in manipusent, you need some example to work with. So we need an example list, and I'll say I want the length of that. Now I'm not going to give it a name, but I'll just say length of this example list. When I do that, we see something happens, right? In our code, we see that we have our length of our example list here. Manipusent gave it a name, but then also the length function was undefined, so it created a blank length function for us. It said length of who knows what x1 is, I don't know yet. This is a whole, it's just a filler for expressions. Now on the canvas, what does this look like? Well, I'm going to move the example above the binding here. So on the canvas, we see we have the tangible value for length. Right now it's returning question mark. We'll talk about that in a second. And then the length function itself is represented like so. So we have the name of the function. We see that it has arguments here. I'm going to name the first argument list. And then next to it, we have the function IO grid, which is showing the inputs and outputs to our function. We see that we have one input right now, one example input, which is this list of length 3. And right now it's returning question mark. Below this, we have it's really a sub canvas. This is where the bindings inside of our function are going to go. And then at the very bottom, we have a tangible value for the return expression of the function. Right now, the return expression is just this whole expression here. And the whole expression returns a kind of a whole value single question mark. So this whole value is just going to be threaded through our code. So that's why the output of our length function right now is question mark. Okay. So one thing we might do when is we know we want to figure out whether it's empty list or not. Right? So in functional programming, lists are often represented as these as linked lists, where a list is you can only pull off the front element every time. That's the best you can do. And the way to see that suddenly is to destruct the list. We're gonna pull the list apart and pattern match on whether it's empty or not. So I hovered over my list and I pressed the struct function, and it indeed inserted the pattern match into my program, where there's one branch for what we do if the list is non-empty, and one branch for what we do if the list is empty. On the canvas, we see that we're in the non-empty case, and we can see that it's named, it's given names to parts of our list. So the front element of our list is bound to the head name here, and the rest of our list is bound to the tail name here. And now there's two return expressions, because there's a return expression for the non-empty case, and there's a return expression for the empty case. And we are in the non-empty case, so the empty case is grayed out. To do length, we want to find the length of the rest of the list, the length of the tail. So to call the length function, we will go ahead and drag the length function into itself, into its bindings. And we see now that we have a call to our length function, but we don't know what we're calling it on. So we're calling it on hole. We can fill in that hole in a second. Notice that this length function is outside of the pattern match. That will need to change. But guess what? It will change, because when we say we want to call length on the tail, when I grab the tail value, drop it into the argument. Now we're calling it on the tail, and Manipusynth reordered our bindings by putting that binding into the appropriate branch in our code. We can see in the function IOGrid now there's several calls to the function. The function is being called with lists of successively smaller lengths. If we want to focus one of those call frames, we'll just click on it. So now we're looking at the case where the list is empty. And in the case where the list is empty, we know we want the length of the list to be 0. So we'll just go ahead and right away say that expression should be 0. We'll focus the next case over, where we have a single element list. We'll see the length of the tail for that list is 0, as we want. And now we want to say we want to add 1 to that. So our return expression here, it'll be 1 plus, oh, now this is interesting. Let's look at these autocomplete options here. You'll see a lot of colors. All these items are colored. What actually these autocomplete options are, these aren't just expressions. These are referring to the values that are on the screen here. So if I scroll down to this one, this maroon 0 is the return value from this call to our length function here. And that's the one we want in this case. So we can actually autocomplete to that, autocomplete to the value. And then when we hit return, it inserts the appropriate expression for us. So I believe the function is now correct. And we can verify that by looking at our IO grid here, seeing that for list of length 3, actually we're returning 3, list of length 2, 2, 1, 0, and so on. All right. So that's one way to do it. There's a couple variations here of other Manipusynth features I want to show. So let's go ahead and I'll just go ahead and do that.
Yes. Can I ask a quick question before you show a couple more features? So could you talk a little bit about your kind of user interface design choices to kind of keep the code separate from the canvas? So I think, presumably the idea is that you don't always need to look at the code, but like in this demo and in certain cases, the programmer might want to or need to follow along. So could you talk a little bit about like maybe the trade-offs and having the code box kind of in a separate place in the canvas?
Yeah, so I can tell you, I'll tell you one thing is, when I sat down to do this work, I asked myself, can we just combine them? Can we just mix these things right together? And immediately, can we do this right inside, right inside VS Code, where we have the values just showing up right in here, right? And just as a discipline, I realized that it wasn't going to be it might be work. Like in 5 years, I imagine these things could be merged. But I chose not to pursue that because I realized that it actually changed the way I thought about the problem. And I needed to keep them separate, just as a way to think about what was possible. So the actual reason that they're separate is because it was like a discipline for trying to be creative with the problem. Trade-offs, well, you have to look at 2 places. And as we'll talk about in a moment, this view over here actually does contain almost all the information that's in the code over here. So you can almost get away with hiding this code in this case. Does that answer?
It does. And so maybe to paraphrase to kind of get the sense of what you're imagining. So even though like the idea and in the future, both modes ought to be like on par with each other, as you're trying to kind of figure out what's even possible, you seem to be prioritizing the kind of value-centric mode more than the code mode. And so even though eventually they ought to be on par. Really, that's the primary mode that you're focusing on.
Yeah, yeah, and just to be utterly practical, there's no way something like this could have traction in the real world unless it was inside the editor here, right in the midst of the text, because people are just so used to text, they're never going to jump to something so different like this. Yeah. Okay. Where were we? Oh yeah, so we're gonna do, there was a couple features I didn't exercise here, so we're gonna quickly do parts of this function again. So if I delete the function, it should reset it for me. There we go. Again, we'll want to call this list. So, and we want to recurse as before. Now, before we had to, the last time we did this, we pressed the destruct button to insert the pattern match. We can, why is this? Oh, shoot. You're just confused about, they got a, I didn't save this, so now it's out of sync. 1 second here. Save, compare. How do I choose which one? How do I do this? There we go. We will just delete this, save this, overwrite, and then delete this. There we go. Okay, sorry about that. Now they're in sync again. That's another reason you want to integrate the two, is so you don't get synchronization problems. So another little trick we could have done, instead of clicking on this and pressing destruct and doing the pattern match, we could have done that a lot quicker. So we inserted the length function here. We could just actually grab the tail of the list. We're grabbing the sub value of the value and dragging it right to our recursive call. And that automatically inserts the pattern match for us and then puts the binding in the appropriate place. So that's one way to do it. An even faster way is, well, here I am. Again, my function is completely blank. I'm going to type in the return expression. I'll type, oops, not there, here. I'll type 1 plus length. We want to do the length of the rest of the list. If we look at the autocomplete options again, we see that actually this sub value is one of the autocomplete options. So we can just go ahead right away and say, I want to take the length of the sub list. And now we very quickly built out almost all our function, just have to make the base case 0, and we're done with that. All right. Final example, let's do this with program synthesis. We're gonna actually delete everything, start over. This time, we'll say length. We want length of that list again. But instead of just saying, oh, we have an example value, this time we're gonna set up an equality saying that should be 3. Mid% will take this, turn it into an assertion in our program. So we see that there's an assertion in our program that says that should be 3. On the canvas, it's rendered as follows. It's in red, meaning it's not satisfied with this X here. And then it's showing us two things. On the question mark here is the actual return value, because the function doesn't exist yet. And then in blue next to it is the value we wanted. We wanted 3. All right. And I'll name the argument list as before. Let's press the synthesize button and see what happens. All right. Hey, we got some code. Maybe it's right. Well, we can look at the code to see if it's right, but we can also look at the function IO grid and see that for every single list, it's returning the value 3. Well, this is what program synthesizers sometimes do. They aren't always super smart. Somehow it figured out to return 3 in the base case, and in the non-base case, it says length of the tail. Well, we don't want that, so let's tell it to try again. Ta-da. And now it has given us a second result, and this result looks right. We're 3, 2, 1, 0, and we can see in the code that it's length tail plus 1. All right. Let's jump back to Keynote. Is it showing me my build thing? Let's just restart just to make sure. All right, so what did we see there? We saw a drag to extract interaction where you could actually take a sub value and drag it into your function to induce a pattern match. We saw auto-completing to values. We weren't just auto-completing to expressions, it showed the value itself, so you didn't have to think as hard about the expression. We saw auto-completing to extract a sub value, so we could do the introduce the pattern match in one less step. We saw assertions, which allowed us to perform program synthesis. Right. So as a quick second example, just to show you, giving you a little more flavor of Minute%, we'll run through a treefold recording that I've already done. On the left here, you'll notice that when you have a tree-like data structure in your program, manipsynth will actually render it as a tree, which is very nice. And the reason we're doing tree fold is that actually sometimes it's kind of hard to think about folds. Sometimes it's easy to get it wrong in your head. So what the fold function is, there's going to be an assertion. We want to fold. We use list.cons starting with an empty list and that tree. And we should get the result 1, 2, 3. So it's going to pluck out the 3, 2, and 1 in our list. What is cons doing? All cons is doing is putting this element on the front of the list. So we're going to cons this element on that list, and then cons 2 on that result list, cons the 1 on that result list, and we'll get 3. And this is all very abstract, so it's a little bit hard to think about, which is why the live values are a little bit helpful. So we're going to get the zoom controls out of the way, and let's go. All right, so I'll make the type. First of all, the type for this tree. And then in the toolbar up top, it actually looked at my type and it just gave me a bunch of example values based on following that's the structure of that type. So when I click on one of these, it's going to immediately insert an example into my program that I can use. All right, here I'm going to edit the example, so it's leaf 1, 2, 3. And then I'll give that, that example call. Right? I gave it as an assertion. I'm not going to use synthesis, but I gave it as an assertion just to help me think about the problem. Right? I'm so used to hitting spacebar to stop, pause, and play videos. All right, so I'm going to rename the arguments. We're going to rename the arguments to the function just to help us think about this. And then we'll drag the function into itself, and we're going to recurse on. We need to recurse on the left subtree. So I'm grabbing the left subtree there, the leaf 3, and putting it into our recursive call. Right. So that introduces a pattern match, and whatever the result of that is, we're going to call that the, did I say left? I meant right. So we'll call it right folded. We'll focus that call frame on folding the right of the list. Pull the cons into the return. Now we folded the right appropriately. You can see that here. The right is giving us the list 3. And I'm going to move some things around just for my own sake. And then now I'm going to think about, okay, I know I need to fold the left side. So what I'm going to do, I think I have to just go ahead and fold. And then, oops, I made a mistake. My program is on fire. There's a type error, but it was an easy mistake. I just needed to put the function as the first argument. And then I can quickly verify that I've gotten it right. So if you haven't written a fold before, I know you probably couldn't follow all that. But that's just demonstrating what this looks like on a slightly more complicated example. All right, so that was tree fold. That was our demos. Let's quickly talk about a few of the implementation details. We'll talk about the interpreter we use, an algorithm to reorder the bindings, and then a little bit about our process for the synthesizer. We used an existing interpreter for OCaml, and then we adapted it by adding this tracing, where we, on every execution step, we log the expression you're at, the call frame number, the value that was the result of that expression, and then the execution environment. And we couldn't modify the standard OCaml tools. OCaml does have an interpreter, but it performs type erasure, and you can't inspect a value when you're at a polymorphic type, which is a problem for our setting, because your functions start out untyped, and we want to still show the value. Right. For reordering bindings, this is the algorithm we follow. We're going to keep track of the variables that are in scope so far. So say we have this binding let x equals right-hand side. We'll check the free variables of the right-hand side, see if any of those variables can't be resolved to the variables that are in scope so far. We're going to look for later bindings that define those names. So like if our binding was x equals y, and y is not defined up here, we'll look for a later binding that defines y, like this one here. And then we'll move that one into scope. So we're going to flip the order here. So now suddenly y is in scope for this binding here. And then we'll repeat for that moved let binding. So we'll look for the free variables of z and repeat. That's our binding reordering algorithm. Actually, it should probably be slightly different, but you can ask questions about that later. The synthesizer, what is our synthesizer doing? It needs to fill in a function or fill in a hole given assertions. There's no big ideas with our synthesizer. We're not doing anything fancy or new, but we just needed to make some choices with the synthesizer so that it can work with few examples, no type annotations, and still produce quality results, even when you already have a bunch of functions in scope. So sometimes synthesizer benchmarks, they only put 1 or 2 functions in scope that they need, but we need to work with a bunch of things in scope from the OCaml pervasives module. All right, so we didn't start from their code, but it's inspired by the myth synthesizer, which does term-directed guessing. So we're going to keep the search space smaller by only guessing type correct terms. And then to do that, when we have a when you haven't typed your function yet, we're going to actually speculate a function type to guess in. To produce better quality programs and to hopefully make the guessing process faster, we have a simple statistics model, a probabilistic context-free grammar. So it will, for example, say that if you use a variable that was more recently introduced, it'll say that that program is more likely. And then there's several other final heuristics like, oh, you have to use all the function variables that are introduced. Right now, the synthesizer doesn't reorder bindings, which is probably the biggest limitation that we have to fix. Right.
Brian, a quick question. I think about the binding reordering algorithm. Is shadowing allowed? A question
oh, yes. Yeah. So that's why I have this thing crossed out here. So the way it would work is there's no difference between what I've crossed out if shadowing is allowed and if shadowing is not allowed. I was trying to preserve shadowing, which is why I did it wrong the first time. But if the way it should work, the way it doesn't work, but the way it should work is that at the same nesting level, if any of the variables at the same nesting level are the same name as the one you want, it will move that one into scope. And if there's none at the same nesting level, then it will look higher. And so in that case, it's not shadowing.
Well, you have to be careful about the term nesting level because each let defines a new nesting level.
Yeah.
Right? So you can say let x equal 1, and then you can say let x equal 2 if you allow shadowing.
Right. So what we have to do, what I mean by nesting level, and I think you understand what I'm trying to get at, is
if you don't have shadowing, you just sorry, if you don't have shadowing, you can just use a graph algorithm on the let bindings, right? I mean, you don't need this kind of scan forward, scan backward kind of stuff, right? It's just the program, it's just the data dependency graph that you get from the variables.
Right, exactly. And so that's how it needs to behave. The reason why we're doing a binding reordering rather than just making it a we want it to behave as if you wrote let x, y, z equals such as this, that it would behave as one single mutual recursion. That's how we want it to behave. But the reason we can't do that is just because of the way OCaml handles certain things. Like if it was in Haskell, maybe we would have done it like this. Because OCaml won't, yeah, that's why. So this is how it's supposed to behave, and that's what I mean. That's what I'm trying to say. All right.
Not sure I understand, but I will, maybe we can talk about it offline.
Yeah, sure.
It's not critical, so.
Yeah. All right, to see if this sort of worked, we did 2 evaluations. One was 38 examples implemented by an expert, and then we also did an exploratory study with 2 professional OCaml programmers. Our example corpus was 38 functions drawn from the first lessons of a functional data structures course, covering natural numbers, list functions, binary trees, binary search trees. And the expert implementer implemented all these functions, but the code editor hidden actually, unless there was some problem. And I didn't use synthesis just to constrain how I was doing this and how I was doing these. Overall, well, oh, you can't see this because the Zoom controls are hiding it. Sorry. For the people in the room, there we go. So it took about 4.5 hours, and there were 3 tool crashes, but it did work. Like you could actually do all these without build all these functions in Manipusynth without reverting to very few reversions to text editing. Fastest function was list length, of course, could do it in 1/3 of a minute. The slowest was a binary tree join, which took 62 minutes, 82 mouse interactions, 64 keyboard interactions, 51 uses of undo, redo, or delete. No type errors, thankfully, but two tool crashes. And this is what it looked like at the end. We'll come back to that. So some observations from this, you could actually hide the code and it worked, unlike Sketch and Sketch. Didn't have any trouble. I don't remember having any trouble with binding order. There was some trouble with the nested match order when she had a bunch of nested matches. But probably the more interesting observation is that there seemed to be this thing where like when you're working with the code, sometimes you start thinking about the values and sometimes you start thinking about the expressions. And when you're thinking about the expressions, you end up not thinking about the values so much. It's going to almost be mutually exclusive. So despite trying to pay attention to the values when implementing all of these functions, found myself often just only thinking about the expressions. And I bring this up because it also came up in our user study, right? So like, why is this? Why do we keep reverting back to thinking about the expressions? Is it because language is great for thinking about abstractions? Is it because we're programmers and we have lots of experience thinking in expressions? Or is there not enough live feedback in the tool? Do we not have enough values out there? All right, so we also did a user study, an exploratory user study with 2 participants. We worked with each for 3 sessions. Each session was 2 hours each. The 2 participants had 5 and 11 years of professional Camel experience. They ran it on their own machines and they chose to use Vim. And then it was kind of like a guided thing where we'd show them what to do. We'd have them work through the same kinds of exercises as the expert implementer. And then they'd answer questions about their experience. Varying amounts of guidance. We did want to see how do they interact with the live values? Do they work non-linearly? Do they interact with synthesis well? How do they interact with their text editor? Are there pain points? Can they complete an exercise without guidance? And are there any other qualitative insights that we gain from using the cognitive dimensions of notations framework? And then our goal here is qualitative insights. We weren't really trying to get any quantitative results. We just wanted to see where can the system can improve. So I mentioned this expression-oriented versus value-oriented thinking. This did come up in the user study, right? So for example, the second participant didn't realize that they were working with live values until after the very first exercise. Like, it was right there on the screen. They were working with the live values, but they didn't realize those were live values from the code. I guess I don't know why. Maybe it's because programmers are so used to not seeing live values. There was another time where we were stuck on a bug, and then when we finally found the bug, we realized, hey, if we'd just been looking at the live values, it would have been obvious what the bug was. Apparently, we were not looking at the live values. We just kept thinking about the expressions. And then the second participant, he really liked those trees that were not drawn as nice trees, but he just said like, wow, there's something subtle. I just found myself wanting to read the serialized text, even though it's clearly uglier. Right? So something about the experience with so used to text. Right? I'm gonna gloss over the other bits of the other observations. I suppose the biggest thing here I'm going to talk about is how do users interact with their text editor. We had them using Manipusynth most of the time, and if they got really stuck, they would maybe flip something around in their text editor, especially if there was some sort of type error and the tool crashed. And the participant one estimated they spent about 40% of their time looking at the text in Vim rather than the Manipusynth display when they were trying to figure out what was going on. And in general, I got the impression that they did feel more comfortable in their text editor. Pain points. There's so many colors on the screen, and it's not always clear whatever all the little pieces are. It's not always labeled. So there's a lot to keep track of. And that's probably had to do with why the participants still, even at the end of the third session, still needed some help. Mostly, like, both of the participants did seem to be pretty comfortable with the tool, but there's just, there was no reference manual or anything. I had to ask the facilitator for help sometimes. Some other final notes. One of the participants missed having comments because there's no comments in the two-dimensional display. The other one didn't care. There's a few things we identified that were a little bit hard to do. Like if you have an existing expression and you want to wrap it entirely with a new expression, that was a little bit hard. And then there was this problem with some things were just not visible. Like if there was too much, it was taking up too much screen space. There was at least one bug where the live value that would have shown us where the bug was, it was actually off screen because it was taking up too much space. So what are our takeaways from these evaluations? So despite the live values, there does seem to be some bias in programmers towards expression-oriented thinking. Why? Great question. And you might think that having this live values would help with algorithm design, but there was never a point in the study where that clearly happened, where it was like, yeah, having the live values here helped me think about the algorithm beforehand. Debugging, on the other hand, that's a different matter. All right, you could almost hide the text editor. Users had no trouble writing assertions. In fact, before we even introduced synthesis, they kind of wanted to write assertions. And maybe Manipusynth could be a little more self-descriptive, but in general, it seems to be working okay. How do we encourage value-oriented thinking? Well, maybe instead of variable names, we can display the values instead, just kind of flip them around here. That's one idea. And then maybe we can have more actions on the values. And how are we going to come back to display? Like, look at this guy. This is the B tree join, the one that took me an hour to do. It's taking up a lot of space. How are we going to come back to display? I mean, one thing we need to do is, like, if you have a large tree, just make it smaller. It doesn't scale them. And maybe the tool maybe we can have more tooltips. All right, so that was Manipusynth. Value-centric and nonlinear programming environment that has synthesis interactions to provide a bimodal programming environment for facilitating general purpose programming of output. Now, it looks like we have a lot to go over yet. That's not true, because we're going to zip through these in like 2 minutes, because there's not, don't want to say a lot about them. We did a couple extra systems that might help in the future programming environment. One is for directly manipulating value text, and the other one is for directly manipulating expression text. And here's the problem. If you're displaying all the values in our program, some of those values are going to need custom visualizations. So how are you going to make it easy for users to provide custom visualizations? So here's an example. This top here would be the generic representation of some value, but there is a more specific, domain-specific representation, which is here. It's an interval on a number line. So maybe an easy way to provide custom visualizations is to leverage two-string functions. Programmers already write two-string functions. And so that's what we did. We built a system that traces the execution of two-string functions and then turns that two-string function into a little structure editor, right? So here's the example. I'm editing the result of the two-string function, and it is changing the original value. So you can change it from a finite boundary to an infinite boundary, or you can change the number there, etc. And there we go, change it to a finite boundary. Right. The other thing we explored is direct manipulation on text. How might you quickly invoke refactorings? And so the system we came up with is this thing where you structurally multi-select the different elements in your code. And based on what you've selected, we can show a short menu of refactorings, of only the refactorings that apply to your selection. So it's a short menu, easy to select what you want. And then use a few defaults just to give you 1 or 2 options for each of those refactorings. So here it is, being implemented quickly. You can see there's lots of items in the code you can select. You hold down the shift key and it just suddenly lets you select items rather than regular text. And then when you select the items, it shows you possible refactorings. And then you can choose a result for those refactorings. And from our user study on this, we discovered that this system, compared to more traditional refactorings, might be better for learning, might be faster once you learn it. And when we gave the users the option to just mix or match using either the old way or the new way, they seem to use this structural multi-selection more. All right, bimodal programming, does it satisfy test-allows principles? Detect failure and fail gracefully. We get small steps, limited inference each time, make it easy to correct the system. It's always text editable. Are we encouraging trust? It's just an ordinary programming language. It's unambiguous what your code is doing. Partial automation, well, you can mix and match between either mode. Although, as I said, our goal today was to see how much you could do without mix and matching. Then finally, for the bottom line value of automation, is it actually providing value? We wanted to have enough output manipulations that you don't have to do as much text editing. So I want to thank many, many people, Sketch and Sketch crew, my family, my church and Graduate Christian Fellowship family, my office peeps, my committee, and my advisor, Ravi Chugh. All right, thank you, and I'm happy to take questions.
Great, thanks for a great talk, Brian. Any questions from the abyss here on Zoom or in the room?
Hey, let me see. Brian, can you hear me?
Yes, I can hear you.
Yeah. So for the manipulative things, so I'm. It looks very magical, but to be honest, I was kind of lost in the middle. So is it like this is particularly helpful for kind of data structure related coding?
Yeah, that was what we were targeting with data structures. Yes. You would, if you wanted to target other kinds of code, you would need to have custom visualizations for it. So we didn't do anything with, say, imperative code. code that, prints things out. It's just functional data structure manipulation for now.
So do you have a, how to say, like a statement, about, for what particular type of computation, this interface helps, and for what type of it does not?
Well, I can definitely tell you that's actually an interesting question, is what are the different things kinds of code that people write? And at one time I tried to look for literature on that, like someone who just listed out all the different kinds of programs that people write, and I could never find it. But I can tell you that it won't help with imperative code, like you need to do this and then do this and then do this. It will help with functional code, which is functional data structure manipulation, which are the examples of that sort of thing are this list here, manipulating binary search trees and stuff like that.
Okay.
And part of it has to do with the goal of being nonlinear, right? So if you're doing imperative code, then what you're doing is linear, and you do have to think about ordering. And we wanted to make it nonlinear, so that fits better with functional programming and functional data structures.
Josh, do you want to go ahead?
Hi, Brian. The Manipasynth is a very interesting tool, and I think this insight into like value-oriented versus expression-oriented thinking is also very interesting. I'm wondering if you've thought about how to kind of smooth the progression or like, kind of playing between those two modes of thinking. I could imagine, right, like maybe partially abstract values. Like if I'm computing the length of a list, I don't really care if the values are zeros or 1, 2, 3 or whatever. What I care about is how many values there are. I can imagine like, values have kind of a high cognitive overhead because there's so many specific pieces, and expressions kind of trade that off for a lighting detail. So I don't know I'm curious if you thought about how to maybe integrate that into Manipasynth.
Not completely. I can give you a partial answer to your question, which is that so here, for example, we're asserting on literal values of 0, right? And you're saying in this case, I don't care what the values are. There are a couple of synthesis systems that let you just put in these polymorphic values that you can only use them as atomic values. Like they don't have any of their properties other than they're a value. I don't know what they are. Manipasynth doesn't support that directly, although you might be able to coerce OCaml's polymorphic variants to do that. Yeah, thanks for the question. Any questions in the room?
There's a couple comments in the chat. Marie or Miriam, sorry, I'm not sure. I bet preferring text over GUI is based on familiarity, like people who learn to type on QWERTY but don't want to switch to other keyboards. And Justin loves the non-linearity. It just makes for a delightful environment. One question I had, Brian. So far you've kind of built two, very different, big bimodal systems like this. I wonder if you could tell us about the kind of any similarities in the techniques underneath, because in the future we're hoping that bimodal programming could be a more general and kind of commonplace functionality. So what kind of has your experience been so far in identifying common techniques that will work in 2 and 3, 5, 10 domains versus how many of the techniques are currently special case to specific application domains?
Yeah, probably the biggest common technique is to use dynamic program tracing. So you run your code through an evaluator, and the evaluator is remembering what happens on each execution step somehow. So that's probably the biggest common technique. Big open question is how to scale that up to large programs. People have done things where you can run a large program and say deterministically replay the program, or there's like the omniscient debugger, I believe, that can let you walk backwards in time. So might be looking at some of those for some inspiration, but definitely some engineering work to do to make the tracing scale. Blaze, yes.
So when you presented the principles a couple of times, you pointed out that the encouraged trust by presenting a model users can understand,
Mm-hmm.
you felt was satisfied by, well, it's just a normal programming language and you have access to that. And I'm curious of like, if you could ruminate on that a little bit more of like, what is user understanding? Like what kind of trust are you trying to engender? Like what could user understanding mean here? And oh, well, there's just also the normal programming language here. Is that necessary? Is that sufficient? Like, the other aspects, and maybe like in the context of like, expression oriented versus value oriented, like how does that impact trust? Very broad question.
And Brian, could you briefly paraphrase?
Yeah, sorry. It was a tough question, so I ended up starting thinking about it. But he was asking to ruminate on what it means to encourage trust in presenting a model, what it means to present a model that users can understand. Is text really just sufficient for that? Is there something else? Are the values helping or hurting, or how does all that play together? So it's kind of, I think it was also kind of a broad question too, but to think about, and I'll say that, yeah, so you do want, just saying there's a programming language there, you can do better than that. Yeah, you're right. You can do better than that. So one thing, for example, in Sketch and Sketch is when you hovered over a item in the output, it would sometimes highlight a corresponding expression in the program, and that can help get with the understanding of what corresponds to what. Another thing, we had at one point in the user study, the user accepted a synthesis result, and it was actually, it satisfied the assertions, but the code was wrong. And it was very difficult to tell that the code was wrong. And one thing that might have happened is if the synthesizer had said, oh, it's very ambiguous for this particular expression in the program, I could have satisfied this with a ton of different things, then we would have realized that, oh, there was actually a problem here. There was part of the code that we weren't hitting. So a technique like that could also help as well. Yeah. Other questions in the room? Casey?
How do you imagine like managing a large 1,000 lines?
Yeah, how do we manage large programs, 1,000 lines or more? So that's where having the panes not be quite so separated would be helpful. So like when you scroll one, you could scroll the other as well. That would help. The other thing that helps is if you can, once you're done with your function, maybe you can collapse the function and only see the inputs and outputs or something like that. So just having variable levels of visibility, that would help a lot too.
I had another question. So in Manipusynth, you kind of showed a bunch of different user interface kind of techniques and ideas for various parts of this programming workflow. You have this kind of like nice, pretty like fountain of lambdas to kind of distract the user when the synthesizer is taking too long. You have these nice like visual examples, concrete values. There's lots of different kind of features that need to go into this entire bimodal system. But now that you've kind of experimented with some of those features, can you imagine some of them being ported to other settings for more traditional kind of IDs where you're working with expression text, but can any of these user interface techniques help augment like a more traditional workflow?
That's an interesting question. I think the thing I think of more so is how would you merge these two sides together so there isn't so much separation between them. I think some versions of the web inspector, for example, when you have JavaScript code, it will sometimes just show the value right next to the JavaScript code in certain versions of the web inspector. And so if you move these values straight right into your code, then you can start thinking about maybe we can start to do manipulations on those values. But as I said earlier, like originally I was thinking about that as a way to approach this problem, but realized that it was gonna be too constraining to begin with.
Okay, so it looks like we're over the hour mark. Are there any parting questions? Is baby Havila still here? Do they have a question? If not, maybe they can follow up afterwards. Okay, so I guess if there's no more questions from the public, maybe we can thank Brian one last time for a great talk.
Thank you all so much for coming.